Okay, so this section is called numerical integration. And in this section, we're going to be trying to figure out how to compute definite integrals, but we're going to do it numerically because some of these are too difficult. So we're going to use the midpoint rule, the trapezoidal rule. We're going to be looking at the errors in between of the two techniques. We're going to be finding absolute and relative errors. We're going to figure out when we use the midpoint and trapezoidal rule. And lastly, we're going to look at Simpson's rule. So the question is, what do we do if we want to compute something like e to the x squared? Notice it doesn't have an x there, so I don't have a du. Or the integral of dx over x cubed plus 4. That's easy if this were x squared, because if this were x squared, then I could use a tan inverse, but it's not. And this last one, I know how to integrate the log of x, but I don't know how to integrate the log of x squared. So all of these are difficult integrals. And so we want to be able to figure out how we can do them. And we can do them provided we're looking at what we call a definite integral. And a definite integral is the integral on a finite interval. And basically the integral from a to b of f of x dx is literally just the area under the curve of f of x on the interval ab. So the first method we are going to use is the midpoint rule. Okay, so here's the midpoint rule. And so here I'm going to draw a picture, and I am trying to compute all right, so I want to compute the integral, let's say from a to b and this function is my function f of x. So I want to compute the integral from a to b of f of x dx. But I know from Calc 1 that that's just the area under the curve. So what I want to do is I'm going to take this region from a to b and I'm going to divide it up into n subintervals. So we're going to divide the interval ab into n subintervals. Okay, so let's say, I think I did in the other class, I did 6 of them. So I'll do the same thing here. Actually, maybe I'll just do 4. Okay, so I have 4 subintervals. And so inside each subinterval, so notice I have this thing looks like this. And then here it is here. And then here it is here. And there. Okay, so inside each interval, I'm going to choose a point, and that point M1, M2, M3, M4, or whatever it is the midpoint. So in general, I'm going to take, I'm going to take a line like this, and I'm going to divide it up into n equal subintervals. And then I'm going to find the midpoint M1, midpoint M2, midpoint M3, dot, 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 midpoint Mn minus 1, midpoint Mn. So I'm going to find the n midpoints, and then I am going to go up all the way to f of that value. And then I am going to draw a rectangle that has the same height as f of mn. So I'm going to go up here, find f, and then go out to here like this. And now I have another rectangle. This one, I'm going to go up. I'm going to go over, find f of that value. That gives me an interval. And then I'm going to go up here and find f of this value. Okay, and so now, as you can see, I have 4 rectangles, or it would be n rectangles if I were doing this in general. Okay. All right, here's another rectangle. I'm not going to color them all in. Okay, so what is the length of the interval? Well, the length of the interval, we already said, is delta x. All right, so the area of any one of these rectangles, the area of the first rectangle is to take f of the M1 and multiply it by delta x. That's the area of the rectangle. All right. The area of the second rectangle is f of M2 times delta x. And the area of the kth rectangle is to take f of mk and multiply it by delta x. So for the midpoint rule, where I have n subintervals and n midpoints, I'm just going to sum these all up. So it is A1 plus A2 plus AN. That says take f of M1 times delta x plus f of M2 times delta x, all the way up to the last one, which is f of Mn times delta x. So as you can see, I can factor the delta x out. And what I am left with is just the sum k equals 1 to n of f of xk. Oop, not xk, I apologize, mk. Oh, I already took out delta x. Okay, so that is the midpoint rule. All right, so the midpoint rule, which is going to give me an approximation to the area under the curve, says find the midpoints of every interval, evaluate to find the height, that will be f of that value, multiply by the width, which is delta x, and then add them all up. And that looks pretty good. That's a good approximation to the area under the curve. So we get this formula right here. That the integral from a to b is being approximated by what we call Mn. Mn is delta x times the sum of all the k equal 1 to n of all f at the mk's. Here, again, delta x is b minus a over n. So you take the length of the interval, and then you divide by n, and that gives you what delta x is. So delta x is b minus a over n. All right, let's do an example. All right, so we want to do the integral from 0 to 3 of x cubed dx where n is equal to 4. Okay, so basically what we're doing is we're going to say that delta x, which is b minus a over n, is going to be 3 minus 0 over 4. So delta x is 3/4. Okay, so what does that mean? That means that I take this length from 0 to 3, and I'm going to divide it up into 4 subintervals. Now, the first one is 3/4. Add 3/4 to that gives me 6/4. Add 3/4 to that gives me 9/4. And add 3/4 to that, that gives me 12/4, which, oh, that is 3. And I like it when they all have the same denominator. It's going to make your arithmetic much easier when they all have the same denominator. Okay, so now I need the midpoint. So how do you find the midpoint? In order to find the midpoint, you take the two endpoints, add them together, and divide by 2. So I get 0 plus 3/4 is 3/4 divided by 2. That midpoint is 3/8. I get 9, 3 plus 6 is 9. So I get 9/4 divided by 2. So that is 9/8. I get 6 and 9, that's 15. 15/4 divided by 2 is 15/8. And then 9 and 12 is 21, 21/4 divided by 2 is 21/8. Okay, midpoint rule. So far, so good. How's everybody working on this? Okay. So my formula says, in order to find M4, which is the approximation to that integral, I have to take delta x times the sum of these. So I need f of 3/8 plus f of 9/8 plus f of 15/8 plus f of 21/8. So I'm using the midpoints. In this problem, this is M1, this is M2, this is M3, and this is M4. And what is our function f? Well, here it is. F is x cubed. Okay. So M4 is delta x. Well, delta x is 3/4. And so I need f of 3/8. So f of 3/8 says put it in here. So f of 3/8, just so I can just write this for a moment. F of 3/8 is 3/8 cubed. Okay, well, I took the liberty of calculating those for us already.
All you have to do is shift it to neutral and activate with the push of a button. When the car does that for you, that's amazing. What's up, YouTube? Welcome to the podcast. I have another video. The HBO special help.
Okay, so here is f of 3/8. If you cube it, you get 27/512. F of 9/8, 729/512. F of 15/8, 3,375/512, and f of 21/8, 9,261/512. Okay. So therefore I get 3/4 times 27/512 plus 729 over 512 plus 3375 over 512 plus 9261 over 512. Okay. All right, so now I get 3/4. I can bring out the 1 over 512. And that gives me 27 plus 729 plus 3,375 plus 9,261. And this turns out to be 3 over 2,048. Times 13,392. And if I am doing this on a test, then I would go to the side and multiply 3 times 13,392. And I would get 40,086 divided by 2,048. And this is approximately 19.617. Okay, so that is my approximation to the area under the curve, or the integral from 0 to 3 of x cubed dx. That's my approximation using the midpoint rule. Okay, so what's the true value? Okay, so let's calculate that. So the true value of the integral from 0 to 3 of x cubed dx is 1/4 x to the 4th, evaluated from 0 to 3. So that turns out to be 81 over 4. So the exact value is 20.25. Okay, so now we have an exact value for this. Don't want that color. I want it red. Here we go.
Dr. Lott,
Yes,
where did you get the 1/4 from?
because this 1/4 here.
Yes.
So when you integrate x cubed, remember you go x to the n plus 1 divided by n plus 1.
Okay.
Got it?
Yeah.
Okay. So this is the exact value of the integral. That's the exact value of the integral. That looks sloppy. Okay, so now, since we know this, we can now compute the error, which means how bad is our approximation? How far are we off? Okay, so in order to compute the error, I wish you guys liked learning online, because I like having the available stuff already done. It doesn't work that well in class, but I am 100% sure. No, I shouldn't say 100% sure. I am 90% sure that pretty much everything's going to be in person in the fall. I think, and I hope. Okay, so this is the absolute error is how far off are we? So that's I, which is the true value, which is 20.25, minus the estimated value, which is 19.617. And that turns out to be 0.633. Okay, so that's not too bad. All right. Unfortunately, though, The true error doesn't always tell us how bad we are. So let's look at the relative error. So the relative error says take the true error, which is 20.25 minus 19.617, and then divide that by the true value. Multiply by 100 because we want a percentage, and that gives us 3.13. So we're off by 3%, and that's not too bad. Okay, well, you know, we didn't get 20.25, but the midpoint rule did a good job. So it's not too bad for me to be able to say that's the answer to my problem. Okay, now there are error bounds, which means how big, what's the biggest the error can be? Okay, now again, I am posting these notes. So if you guys don't get a chance to write all of this down, this whole definition, just leave a space and then grab the notes off a Blackboard and fill in the little bit. But I'd rather you pay attention to what I'm doing and what I'm saying, and then just go back and grab the notes and fill in the little words that you may have missed as I was talking. Okay, so here we go. So f of x is continuous. Our f of x is x cubed. That works. It's on the interval AB, which is 0, 3, and it has a second derivative. So notice that this error is going to be dependent on our second derivative. So we need to find k, which is the maximum value of the absolute value of the second derivative on the interval. Once we do that, then we can find a maximum error bound. In other words, this is the maximum our error can be for any n that we use. Okay, so let's compute it for this problem. All right, so let's see. Let's start off with finding f, the biggest f double prime can be. So we're on the interval 0, 3. So we have f of x is x cubed. F prime of x is 3x squared. And f double prime of x is 6x. All right, so the maximum of the absolute value of f double prime of x on this interval, well, that's going to occur when x is 3. So the biggest it can be is 18. And that 18 is what we are going to call k. So that is this k right here, which is the biggest the second derivative can be. Now we also need to find b minus a. B minus a is 3 minus 0. So that's 3. So now we can know what goes in here. And the last thing is n squared, and n squared is 16. Okay, so the biggest the error could be for this midpoint rule is going to be k, which is 18 times 3 cubed, that's the b minus a cubed, over 24 times n squared. Okay, so I haven't calculated that, so let's calculate that. So I get 18 times 27 divided by 24 times 16. 16. Okay, so the maximum error is 1. So this is the max error for the problem. And clearly we are under that. So our error was 0.633. By using the estimate, the maximum error would be 1.2656. So actually we didn't do too badly. Okay. So that is the midpoint rule. All righty. Any questions about the midpoint rule? Using all the midpoints. Okay, why is my thing frozen? Using all the midpoints.
Dr. Lot, is this gonna be in the exam?
No, not at all. It's on exam 4.
Okay.
Yeah. You want it on the exam?
Negative. I think I'm good.
I think it's too much to learn and only have a day to figure it out.
Yeah.
So I try to be respectful of the fact that, man, I didn't even get a chance to ask her a question about it in office hours. The test came up so fast. Okay. So the next rule is the trapezoidal rule. Okay. So the trapezoidal rule depends on trapezoids. Okay. So again, I'm going to draw a function. You have got to be kidding me. Okay, give it a minute. Okay. So again, I'm going to take a function. And here's f of x on the interval from a to b. And again, I'm going to divide the interval into, so we're going to divide the interval into n sub-intervals again. Okay, so now after I do that, this time, instead of drawing rectangles that have the height of the midpoint, I'm going to draw trapezoids. So what does that mean? I'm going to take this, go up to here to f of that height, go to f of, well, that looks ugly, go to f of that height, go to f of this height, and then f of this height. And so then I am going to draw a trapezoid. So now you can see if it goes like this. There is my first trapezoid. My second trapezoid looks like this. My third trapezoid is here. And my fourth trapezoid is here. Nope, that's in the wrong place. That's headed the wrong way. Okay, so as you can see now, I have trapezoids. So here is maybe one trapezoid. Again, I am not filling them all in. I told you guys I hated coloring as a little girl. I like it even less as an adult. Anybody else not like coloring as a child? I just thought it was stupid. Once I did that, I was like, okay, what do I do next? I wish I had an artistic mind. Then I would enjoy it better. Okay, that's good enough. That's two trapezoids. All right. So now that you see the two trapezoids, how do you find the area of a trapezoid? All right, so I'm going to draw a trapezoid, and I hope this does right. That is not a trapezoid. Let's try it again. There we go. Okay, so there's my trapezoid. Unfortunately, it's not perfect, but that's the best I'm going to get. All right, so the area of a trapezoid is A equal to 1/2 base 1 plus base 2 times the height. Now this trapezoid happens to be laying on its height right now. So I'm going to call this side B1 and this side B2 and this side right down here that's going to be its height, which I'm going to call delta X. Okay, so that's its height. All right, so now if I come back over here, notice that for this trapezoid right here, if I make this xk minus 1, and I make this one xk, then this height is f of xk minus 1, and this height is f of xk. So therefore, I get that the area of the first trapezoid is 1/2 f of x0 plus f of x1 times delta x. Where did that come from? Well, again, I took my interval divided it up into a bunch of things. Here is A, otherwise known as x0, x1, x2, xn minus 1, xn, otherwise known as B. Okay, the area of x2 is 1/2 f of x1 plus f of x2 times delta x. So if I sum them all up, so now I'm going to say that my integral from A to B of f of x dx is going to be approximately A1 plus A2 all the way down to AN. So I'm going to call that TN, which is the trapezoidal rule approximation with N intervals. So for A1, I'm going to get 1/2 f of x0 plus f of x1. For A2, I'm going to get 1/2 f of x2, x1, sorry, plus f of x2. Then I'm going to get 1/2 f of x2 plus f of x3 plus dot, 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 plus the last one, which is 1/2 f of xn minus 1 plus f of xn. So now let's look at my formula. Notice that f of x1 appears here and here, so it appears twice. F of x2 appears here and it appears here, so it appears twice. F of x3 is going to appear twice. In fact, f of all the things on the inside are going to appear twice, and f of the first and the last only appear once. So you get Tn. Let's factor out, oh, I forgot my delta x in every last one of these, didn't I? Oh my goodness, delta x plus, oh, Okay, so now I'm going to factor out the delta x over 2. And that's going to leave me f of the first one plus 2 times f of the next one, x1, plus 2 times f of the next one, x2, plus 2 times all of the ones until I get to 2 times f of xn minus 1, the second to the last one, and then only 1 times the last one. And that is the trapezoidal rule. Okay, so Tn, which is my approximation to the integral from a to b of f of x dx, is simply to take delta x over 2, sum up the f of the values of all the ones on the inside, and the ones on the end, you only take it one time. Again, remember delta x is b minus a over n. Okay, so we're going to do this again with this example. Same example, trapezoidal rule. Okay, so delta x is b minus a over n. So again, that's 3 over 4. So nothing has changed from the last problem. However, we're not using midpoints anymore. We're using endpoints. Divided by 4. So remember, this is 0. This one was 3 over 4. This one was 6 over 4. This one was 9 over 4. And this one was 12 over 4, which we said was 3. Okay, so the trapezoidal rule says T4 is going to take delta x over 2. Delta x over 2 times f of the first one, f of 0, plus 2 times f of 3/4, plus 2 times f of 6/4, plus 2 times f of 9/4, plus 1 times f of 12/4. Okay. Of course, I took the liberty to find out these ahead of time. All right. So that says T4 is equal to 3 over 4. F of 0 is 0 plus 2 times, well, 3/4 cubed is 27 over 64. Plus 2 times 6/4 cubed. I'm right. I need to write what it is. 2 times 6/4 cubed is 216 over 64. Two times 9/4 cubed is 2 times 729 over 64. And then the last one, only one time, 1,728 over 64. Okay. So if I'm not mistaken, I like fractions, so I was trying to make this simpler for me. So I made everything over 32. So this is 3/4. I got 27 over 32 plus 216 over 32 plus 729 over 32 and 8,000. No, not 8,000, 800. 864 over 32. So now I could take the 3/4, take out the 1 over 32, and that just leaves 27 plus 216 plus 729 plus 864. And that comes out to be, okay, Dawn, I thought you figured this out. $5,508 over 256. And that is approximately 21.516. Okay, so that's the estimate I get using the trapezoidal rule. Any questions about the manipulation of the formula? So I always find these F values first, especially if I know I'm going to be doing midpoint rule. I find them, trapezoidal rule, find them. The ones you use for the trapezoidal rule, you can also use for the Simpsons rule. So, okay. All right, let's talk about error. All right, let's go back. Where's my exact? I did that once, I'm not doing it again, okay. So here's the exact. Okay, so we calculated the exact value before. All right, so now we want to calculate the error. Okay, so the error in this trapezoidal rule T4 says take the absolute value of the true integral, which is 2025, subtract the approximate T4, 21.516. And you get 1.266. Okay. That's not too far off from twice as big as the midpoint rule. The relative error, 20.25 minus 21.516. The absolute value of that divided by the true error, the true value, which is 20.25 times 100. And this is 6.25%, almost twice as big. Okay, so the error in the trapezoidal rule is basically almost twice as big as the error in the midpoint rule. Okay, so let's look at error bounds again. This error bound is very similar. So if I look at the error bound in the trapezoidal rule, as you can see, for the maximum error bound, f of x has to be continuous. But notice, again, we're looking at the second derivative. So we're trying to estimate this based on the second derivative over this interval. And so the error ET, that's error in trapezoidal rule. So there's EM, ET, and ES. The error ET in the trapezoidal rule looks like this formula. And actually you will see that this error is twice as big, and that's what we expected to get. Notice this error is twice as big. The other one divides by 24. This one divides by 12. So this error is twice as big as the other error. So for the other maximum error, we got I don't remember. We got 1.2656. So this is going to be twice that big. Whatever that is, because it won't let me do it. .5312. And notice this error is indeed smaller than that. Okay. All righty. So far, so good. 2 techniques already. Here's the last one. And the last one, I'm not going to derive because deriving it is rather difficult. So I'm not going to derive Simpson's rule. It would take up a lot of our time. Uh-oh, I'm too far down. Here it is. Okay, so Simpson's rule, there is a restriction, n must be even. This will not work if you try to divide your interval into an odd number of subintervals. N has to be even. And then your formula looks like this. So my question to you is, what's different about this formula than the trapezoidal rule? What do you notice that's different? Anybody?
Can you repeat that again? Sorry.
Here's the trapezoidal rule. Okay, and here is Simpson's rule. Anything different you notice? Okay, well, first off, we divide by 3 and not 2. So one difference is it's delta x over 3. And another major difference is these alternate 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, and then 1 times the last one. So the difference with this one is this one's formula, you take 4 times the second, 2 times the third, 4 times the fourth, 2 times the 5th. Okay, so for Simpson's rule, we are going to compute the same integral one more time. Okay. So we're going to again use n is 4. So delta x is b minus a over n. So once again, it is 3/4. Okay, we are going to then divide our interval from 0 to 3. Into 4 equal parts. X0 is 0. This is going to be 3/4, 6/4, 9/4. Whoop, 9 over 14, 9/4. And our last point, which 12/4, which we said was 3. Okay, so again, we're going to use our endpoints to help us get the solution that we need. Okay, so for S4, we're going to have delta x over 3 times f of 0 plus 4 times f of 3/4 plus 2 times f of 6/4 plus 4 times f of 9/4 plus 1 times f of 12/4 or 3. I think I'm gonna leave it 12/4. Okay, so again, I took the liberty of calculating these things. It is the same. Okay, so 3/4 divided by 3 is just 1/4. F of 0 is 0, plus 4 times f of 3/4 is 4 times 27 over 64, plus 2 times 216 over 64, plus 4 times 9 or f of 9 over 64, which is 9 f of 9/4, which is 729 over 64, and then 1 of the last one, 1728 divided by 64. Okay, that looks beastly, but it's not bad. Oh, we're doing Simpson's rule. I'm sorry, I got a little lost. Okay, so 1/4. Take out 1/64. And that leaves 4 times 27. Oh, I just give you the number. 5184 if you add all that up. And this number comes out to be, oh my goodness, 20.25. So how did that come out to be exact? If you remember, this is the exact value. Okay, so will we always get the exact value? Absolutely not. We get the exact value in this problem because when we maximize the derivative, for us, that thing is 0. So first off, the error in this approximation is 0. Okay, so the actual integral minus S4 is 0, and so is this. So why is that 0? Okay, well, the reason why that's 0 is because the error, the maximum error for the Simpson's rule is quite different. So here is the maximum error for the Simpson's rule. Okay, uh-oh, that didn't do right. I want the whole thing. Okay, there we go. So now the maximum error for Simpson's rule, oh, look what it depends on. It depends on the maximum absolute value of the fourth derivative. Okay, so what's the fourth derivative in this problem? Let's see. We started out with f of x equal to x cubed. F prime of x is equal to 3x squared. Okay, so this is 3, come on now, do what you're supposed to do. 3x squared, thank you. F double prime of x is equal to 6x. F triple prime of x is equal to 6, and then the fourth derivative at x becomes 0. So therefore, because the maximum value of the derivative is 0, when I go to calculate my error, which is, oh, I didn't give you the formula. Here it is. So for this problem and anything that is of cubic power, this is the maximum value of ES for this problem. And as I said, for this problem, K is 0. So therefore, there is no error for cubics. Okay, no error. Okay, so I'm going to pause for a moment and take roll. So students usually ask me, Dr. Lott, what are we supposed to do with this on our homework and a test? Okay, so here's the thing. On the homework, they're going to ask you something like, so on the homework, you're going to get something like estimate the integral from 0 to pi of cosine of x squared dx. And so with using let's say M6, T6, and F6. So that means you're going to need to take the interval from 0 to pi. Oh, come on. I'm just, all I want is a straight line. Okay, so the interval from 0 to pi, and you're going to divide it by 6, pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, however it comes. And then you're going to use each one of these, find each one. So for the midpoint rule, you're going to need pi over 3, no, pi over 12. 3 pi over 12. 5 pi over 12. 7 pi over 12. 9 pi over 12. And 11 pi over 12. Okay, so the red ones you're going to need to use for the midpoint rule, and then the black ones you'll use for the trapezoidal rule and Simpson's rule. And you will compute each one, and then you will do the decimal equivalent at the end. And then if it says round it to the 4th decimal place, please round it to the 4th decimal place and put that in, because you're going to do a lot of work to get the answer. And the last thing you want to do is put it in and incorrectly. Okay, so you got to make sure you pay attention to how they want it. Okay, so that's on the, there. So now what about a test? Okay, so we're going to have a test on this. And obviously I am not going to let you use a calculator, because we don't use calculators in this class. I try to give you things that don't need a calculator. So now we're on the test and we don't have a calculator. So what are we going to do? So here's the problem. The problem. Compute this using M6. Let's just say I'd say using the trapezoidal rule. Okay, so then you are going to take the interval from 1 to 4. Divide it up. So what does that give you? That says that delta, oh, it said 6, and I didn't do enough. Get rid of that. Okay, I need 6. So delta x is going to be b minus a over 6, which is 1/2. Okay, so therefore this is going to be 3/2. This is going to be 2. This is going to be 5/2. This is going to be 3. This is going to be 7/2, and that will be 4. Okay. So therefore, you will need to find f of 1, which will be e to the minus 1 squared. F of 2 will be e to the minus 3/2 squared, which will be e to the minus 9/4. F of, nope, that's wrong. This is f of 3/2. f of 2 will be e to the negative 4, etc. Okay. And then your final answer. Dun, dun, dun. On the exam will be this. This is delta x over 2, which is 1 over 4. Then the first one is e to the minus 1, 2 times the second one, e to the negative 9/4, 2 times the next one, e to the negative 4, plus 2 times e to the negative 5/2 squared, plus 2 times e to the negative 3 squared, plus 2 times e to the negative 7 over 2 squared, plus 1 of the last one, which is e to the negative 16. And that will get you 10 out of 10 on the exam. Okay, any questions about that?
So this will be on exam Thursday?
Pardon?
This will be on the exam on Thursday?
This is not, I repeat, this is not on the exam on Thursday. The exam on Thursday covers section 3.1, 3.2, 3.3, and 3.4, and there are 2 problems from each section.
I have a question. You just said there will be exams on all the way up to 3.4, but when you sent out the announcement, it said 3.5. Will there be
No,
questions on 3.5?
No.
Okay.
somebody's reading Blackboard. Okay. Any questions about the trapezoidal rule, Simpson's rule, the midpoint rule, error bounds, anything of the such? I know this section is going to take a minute to digest. So that's why I'm not putting it on the exam. It'll be on the next exam. But so if nobody has any questions on this, I'm going to stop recording.